discussing plane frames now. Last time we dealt with plane frame also, but we discussed frame with sway and non-sway, but using beam stiffness matrix. So this time we will be using plane frame stiffness matrix. Okay, so where's the... This is the local stiffness matrix of a plane frame. Okay, so as you noticed, it's the same with the beam stiffness formulation here. We just added the formula for axial member. So therefore we considered now the axial deformation. The last problem or topic, we didn't include the axial deformation, and we assume negligible deformation in axial deformation. So this today we'll consider the axial deformation. Therefore, even the axial force will be obtained in our problems. Unlike with the beam stiffness formulation, we only get the shear and the moment. Okay, and you can get the axial force by drawing the free body diagram, no, after getting those shear and moment forces. So unlike now with using plane frame stiffness matrix, we can directly get the axial forces. Okay, so this is the local stiffness matrix. Okay, now let's consider an arbitrarily inclined member with theta, inclined theta. And similar to what we did in truss, we will use transformation matrix. So this is transformation matrix in plane frame. Okay, notice that we have 1 here because it corresponds to moment. Q3 and Q6 corresponds to moment. Q1 will corresponds to axial, and Q2 will corresponds to shear. Then Q3 will corresponds to moment. And this is 1 because a certain moment, even if you refer to another axis, it's still the same direction, or yeah, same sign. Okay, regardless of the inclination. Okay, and if you express that in matrix form or in a general formula, that is F equals T transpose Q. Okay, by the way, this is a transformation matrix, this one, sorry. Okay, and again, to determine the global, so earlier we get the local. Now to determine the global, we will use the same formula, T transpose K local T. Okay, so this is the formula we've been using even in beam and in axial member. So it's still the same formula. So if you operate that, you will get, where's the global K? This one. Okay, and this one. So this is the K global. Okay, while this small k is the K local. Okay, and if you operate that, you will get this stiffness matrix, plane frame member stiffness matrix in any inclined axis or theta. Okay, so still 6 by 6, 1 2 3 4 5 6, 1 2 3 4 5 6. Okay, and it's also similar to other definition of stiffness matrix. It's symmetric. Okay, this one, this K12 is equal to K21. Okay, say K15 is equal to K51. K51, this one. Okay, and then so let's try to solve a problem. Example 6, not that one. Where's my, not this one. Okay, so this is a first problem. Okay, this is a plane frame problem. As you notice, area is now given and inertia, of course. Okay, it's a two-member plane frame, so this is also non-sway. I think we solved this already in previously, and so this is the implementation of the stiffness matrix, local stiffness matrix. So since it's already 6 by 6, I now just input the unique data. So for example, the F11 or the K11, I didn't use K11 because I have a K sub I formula. Okay, so just to avoid confusion. Okay, where is our, here, what's that? Let me, this one. So this again, this is the local stiffness matrix, and if you operate the K global is equal to T transpose KT, so you will get this. So let's compare if I properly implemented this formula to our SMAT. Yeah. So there. So F11 or K11 is AL squared over I plus 12 sine squared theta. Okay, so correct. K12 AL squared over I minus 12 here, cosine theta sine theta. Okay, K13 negative 6L sine theta, negative 6L sine theta. K14 negative AL squared over I here plus 12 sine theta. I think there's a square here. There, okay, there's a square. So I'll move it further here. Next is maybe K22. K22, this is K22, right? AL squared over I sine squared theta plus 12 cosine squared theta. And K23 6L cosine theta, 6L cosine theta. And AL squared, okay, K33 4L squared. Okay, so that's it. I think this is good. So this is the implementation of that. So again, how about the coding? So let's proceed with the coding. So this is how I coded or assigned a number. So we have two members, and since it's 6 by 6, that means we have three displacements each joint, right? So I may name this as 1, 2, 3, 4, 5, 6, 7, 8, 9. That means K sub 1 will have 1, 2, 3, 4, 5, 6. Okay, as the code for the DOF, degree of freedom. And member 2 will have 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Okay? Now, looking at the structure, where will this displace? What are the displacements? So we have 3 displacements per node. So 3 here, because you have no restraint here on this joint. And as you notice, we have a pin support. That means it has rotation. It can rotate. No? So we have another one here. Therefore, our S is 4 by 4. We have 4 unknowns. Okay? 4 unknowns. And that code is 4, 5, 6 here plus 9. No? The one corresponding to rotation. 9. Okay? So therefore, the S matrix code will correspond to 4, 5, 6, and 9. Okay? So 4, 5, 6, and 9. And which is this one. Okay? 4, 5, 6, and 9. Okay, and where is our transformation matrix? Cosine, sine, negative sine, cosine. Okay, that's it. Okay. Next is okay, so looking at the code, so I'll encircle the numbers that will be extracted, no? So the code that will be extracted. For K1 we will need 4, 5, 6. For K2 we will need 4, 5, 6, and 9 here. Okay? Okay. So this is important because again, this is what we need in creating our BU and BB matrix, right? So if I rewrite here, BU, my BU matrix is the location of the datas that we need to extract. So for member 1, it's located in 4th, 5th, and 6th, right? So I'll write down for my BU as 4, 5, 6. Okay? Now for member 2, I will extract 4, 5, 6, and 9. So that is 1st, 2nd, 3rd, and 6th. So I'll write down here 1, 2, 3, and 6. Okay. Now for my BB matrix, okay, what's the location? So BB will corresponds to the destination in our S matrix here. Okay. So this 4, 5, 6, what's the destination of that? What's the the position? It's the 1st, 2nd, and 3rd, right? So 1, 2, 3. Okay, while for the member 2, its location is 1st, 2nd, 3rd, and 4th. So 1, 2, 3, 4. Right? So that's why when if I let you look at my BU and BB, that is consistent. Okay, 4 5 6 1 2 3 6. For the BB, 1 2 3 1 2 3 4. Okay. Okay, so we're done with BU and BB matrix. Next is, oh, by the way, so after implementing this, we have here K sub 2 and K sub 1. Okay. Take note, this is already global stiffness matrix because we already considered the theta. Okay, the inclination. Member 1 is inclined pi over 2. Okay. Pi over 2 is 90 degree because SMAT by default is in radian. Okay. 4740 is here. And inertia 22.2. Okay. Then 10 meters, 8 meters. Of course, member 2 will have 0 inclination. That's why this is 0. And okay, so that's my... Okay, next is... So this is my my code for generating the stiffness matrix. Okay, so this is my stiffness matrix. And how about P sub F? How do we derive this? Okay, so let me show you this. First, so this is our structure. Okay, so this is our structure. We have a uniform load here. And a concentrated load here. So what's the fixed end forces for a uniformly loaded? The reaction is WL over 2. So this is 24. Here's our structure here. There. Okay. So 24 times 10 over 2, that's 120. Okay. And for the moment, WL squared over 12. So 24 times 10 squared over 12 is 200. So QF1 is I'll redraw again the numbering. So this is 1 2 3 4 5 6. Okay. So this is 120. In relative to our drawing, where is 120 acting? This one, right? At code 1, which is the positive is going to the right, but our reaction is going to the left because it will counter the uniform load. Therefore, again, this is code 1, so negative 120. Okay, because it's opposite to our direction. So the remember, direction and sign is critical in this stiffness method, right? Next is code 2. Do we have a force from our fixed end forces that will correspond to code 2? None. So that is 0. Okay, it's going upward. So we don't have actual reaction from a uniformly loaded member. And code 3 is moment. Okay, Okay, so which is 200. So this is 200. Okay, so same goes with this, with the other end. So 4 will be negative 120. 5 is 0 because we don't have actual reaction from here. No actual reaction. And moment is negative 200. Okay, so again, take note of the consistency between the direction of the code and to our fixed end forces. Okay, next is for the member 2. We have 75 kilonewton acting on the midspan. So basically, of course, 75 divided 2 is 37.5. While the moment is PAB squared over L squared. So PAB squared over L squared. That's the formula. Or PBA squared over L squared to the other end. Since this is midspan, you can just use PL over 8. Okay. So 75. Again, take note of the direction. We don't have 4. We don't have an actual reaction. So this is 0 at code 4. For code 5, this is vertical. So that's your vertical reaction, 37.5. And for the number 6, that's the moment, 75. The moment here. Okay? So that's your QF1, QF2. Next is we need to, from those QF, we will generate P sub F. Okay? Which is consistent with the code in our S matrix, which is 4, 5, 6, 9. So we'll algebraically add all the reactions or from the fixed end forces corresponding to 4, 5, 6, and 9. Okay, so for example, 4. Let's start with 4. Negative 120 plus 0. Negative 120. 0 plus 37.5. 37.5. Negative 200 plus 75. Negative 125. And lastly, negative 75. So that's our P sub F, which we will need in our formula, right? Because P minus P sub F is equal to this one, SD. So that's our general formula. We now know P sub F. We don't have P vector. We now know S matrix. We can get now the unknown displacements. Okay? So P sub F. Now, if you again, oops, where is that? If we write this, so D is equal to S inverse negative P sub F. Okay. Now, where's our S mat? That's why my P sub F here is this one. So I multiplied that to negative sign. So negative 120, so that becomes positive 120. 37.5 becomes negative 37.5. Negative 125 becomes positive 125, and negative 75 becomes 75. And typing in the formula S inverse P sub F, so we have this displacement. Okay. Okay, next is these are displacement. Okay, and set up the displacements, the displacement vector for each member. Okay, because setting up our, so the displacement here is d1, d2, d3, while this one is d sub 4, the rotation. Okay, so therefore for member 1 you have d1, d2, d3 on the other ends. For member 2 you have d sub 4, side d1, d2, d3, and then d sub 4 also. Okay, so this is the displacement vector qf sub 2. Let's check the consistency. Okay, qf sub 2. Okay, and then qf sub 1. Okay, the same. Then we can now get the member and forces, this formula, k1 v1 plus qf1. Okay, so we now know v1, we know k sub 1, and we know qf1. We can get member and force for member 1 and for member 2, which is this. Okay, so this is the corresponding STAAD file for that plane frame. Oh. Okay, so this is the STAAD file. Loading. Okay, the 24 kilonewton per meter uniform load and the negative 75 kilonewton at the midspan. And check the properties. Okay, so double click this. Again, the given is right. This one. There. So we have 4740 and 22.2. 474 and 22.2. Of course, this is still, no, because 200 gigapascal. Okay. Then post processing. Okay, I need to run again. View. Okay, so minimize this. Actually, this is the SMAT file. There. So for F1, these are the sets of forces. So I'll double click this to get the shear and bending. Okay, so for the bending, we got 222, 155. So that's it, 222, 154.65. For the shear, this is the shear, 56 kilonewton. I'm sorry, 126. Okay, 126, 113. Because this corresponds to code 1, 2, 3, 4, 5, 6. Remember, code 1 is here. So that's the shear. Okay, 126 and 1813. So next is the axial. So in this figure we cannot get the axial, so I'll go to f sub x here, 56.8, that one, 56.8, 56.8. Okay, so the same. So that's the difference, right? In using plane frame stiffness matrix, we can directly get the axial, you know? Unlike with the beam stiffness matrix formulation, we only get the shear and the moment. For member 2, I'll double click this, shear bending. So I got 154 and 72. No, not this one, because that's the other end. So on 154, that's the moment. So for member 2, this is code 4, code 5, code 6. So this is 4, 5, 6, the moment, 154. Okay, so 5 is the shear, so that's 56.8. so if I click this, we should get 56. Okay, so the same, 56.83. For axial, again, I cannot get that here, so that's if I click this, so this is the axial, the fx, 113.185, 113.885. Okay, so that's it. We were able to get all the axial shear and moment in plane frame, non-sway. Okay, using plane frame stiffness matrix. Okay, so let's proceed with another example. This time it's plane frame again, but this time it's sway matrix, sway frame.